This video will explain about flow past immersed body. In this chapter, we consider various aspects of the flow over bodies that are immersed in a fluid. Examples include the flow of air around airplanes, automobiles, your motorbike, or the flow of water around submarine and fish. In this situation, the object is completely surrounded by the fluid and the flows are termed external flow. As you can see in this slide, this is experiment about aerodynamic forces for automobile and then for the airplane that was executed in wind tunnel. Okay, so basically, in order to determine the aerodynamic force such as lift, drag, and then to identify the stability of the car, we need to run the experiment in wind tunnel. Okay, so as you can see in this figure, this is basically in water tunnel. Okay, so as you can see, the wake behind the car is captured by using this laser. Okay, so first I will explain about the learning objective for this chapter. So for the learning objective, first, after completing this chapter, you can identify and discuss the features of external flow, and then explain the fundamental characteristic of a boundary layer, including laminar, transitional, and turbulent regimes, and then calculate boundary layer parameters for flow past a flat plate. Explain the physical process of boundary layer separation. And then in the last part, you can calculate the lift and drag force for various objects. So for introduction, as I mentioned, many practical situations involve flow past object like car, your motorbike, your bicycle. So it is involved with a flow passing an object. So flow of air around airplanes, automobiles, and falling snowflakes, or the flow of water around submarines and fish. In this situation, the object is completely surrounded by the fluid and the flow are termed external flow. So external flow involve air, often termed aerodynamics. So the fluid force, which is lift and drag on surface of the vehicle, such as cars, trucks or bicycle, has become a very important topic. Theoretical and experimental are used to obtain information on the fluid force developed by external flow. So for the theoretical, we can use numerical and analytical in order to find the information about the aerodynamic force such as lift and drag. For the analytical, not all body or not all object can be defined based on the equation. So that's why numerical simulation such as CFD can be used in order to obtain the aerodynamic force for such as lift and drag. So for the experiment, wind tunnel, as I mentioned in first slide, wind tunnel or water tunnel are used for external flow where the scale model is tested. Scale model means that we scale down the airplane. If it is airplane, we scale down the airplane so that it can fit in the wind tunnel. And then for the car, so it is also scaled down so that it can be used inside the wind tunnel. Okay, so this video shows some wind tunnel for Airbus. So this is the real wind tunnel for commercial aircraft.
146 is an aircraft from the 1980s. It's been around a long time, and this wind tunnel model was part of the original design.
So as you can see, the Airbus, the airplane, maybe A320 or A380. So it is scaled down from the real scale of aircraft.
To put those on so that the aircraft looks like E-Fan-X. Well, we're looking really at the overall design of the aircraft, so it includes aerodynamics, where we're trying to understand the forces on the aircraft.
So this is flow visualization based on laser and also test on the aircraft.
And we needed to change the porosity of some of the devices inside the ducts to ensure that they're related correctly to the full-scale E-Fan-X devices.
Okay, so next slide. Now we move to general external flow characteristic. So basically, throughout this chapter, our non-dimensional number for the external flow is characterized by the Reynolds number. So you can recall your MEC 441, where the Reynolds number is defined as a ratio between initial force and then viscous force. Okay, so as you can see in this figure, in order to do the experiment or to do the numerical simulation, we need to identify the coordinate system. Basically, for the external flow, we use a fixed coordinate system that is fixed to the object. Okay, so as you can see, you have incoming velocity. So this incoming velocity, throughout this chapter, we assume it is a uniform. So recall in chapter 2, we have uniform flow. So it is always parallel, and then it is steady in terms of space and time. Okay, so this U for the incoming velocity, it is uniform and then steady in space and time. Okay, so this is for the XY. So mean that it is 2D, two-dimensional, and then for B it is asymmetrical body. So and then for number 3, for this airplane, it is three-dimensional body. Okay, so the shape of the body affect the flow characteristic. Okay, so either the shape it is streamlined or blunt body. Okay, so for the streamline, we can see the real vehicle that has a streamlined body is like kayak. So I will show some a video how kayak move due to the streamline, so we can easily move the kayak in the water. Okay, and then for the blunt object like airplane, like cylinder or like sphere, so it is considered as a blunt body. So for as the flow immersed in water or in around the fluid or air, there are interaction between pressure and also shear stress. Okay, so the pressure is normal to the body, and then another stress, which is shear stress, which is due to the viscous effect, and normal stress due to the pressure, which is P. Okay, so the resultant force in the direction of the upstream velocity is termed the drag. Okay, so as you can see in this figure, for this airfoil, so basically this is airfoil. In this region, in the lower part of this airfoil, the pressure is relatively high, higher than 0. Okay, In this region, basically we call it as a pressure region. Okay, and then at the top side of the airfoil, where the pressure is less than 0. So in this side, okay, in this side we call it as a suction side, where the velocity and the pressure is very low. And then not only pressure, as I mentioned before, we also have shear stress that is distributed around your airfoil. Okay, and then integration between pressure force and shear force, we can come up with the drag, which is in parallel with the velocity, with the coming velocity, and then lift, which is always perpendicular with the incoming velocity u. Okay, so and then this is only for two body, which is drag and lift. If let's say you have three-dimensional body, so you will have another forces, which is side force. Okay, so that was for the three-dimensional. So by integrate the pressure, force and shear force, we can obtain the drag and lift. Okay, so this is as you can see, there is in this figure, let's say you have, this is incoming velocity. Okay, so this is incoming velocity, and then this is your body. Okay, and then the body is inclined with angle theta. Okay, and then as I mentioned, the pressure is always acting towards your body. Okay, and then the shear stress tangent to the surface, or tangent to your body. Okay, so in order to identify the drag force, okay, drag force, as I mentioned, is always parallel with the upstream. Okay, so it always parallel with the upstream velocity. Okay, so mean that in this for the parallel, so this is fx, and then also fx for the shear force. Okay, so summation of change of force in x direction, we obtain PdA. PdA basically is force. Pressure is force over area, and then force is pressure multiplied with the change of area P multiplied by dA, and then cos theta, so it is cos theta for the fx, and then wall shear stress multiplied with dA, sin theta. Okay, sin theta for the shear force. Okay, and then for summation in y direction, we got negative P dA sin theta plus tau w dA cos theta. Okay, and then in order to obtain the drag and lift, we need to integrate this equation. Okay, so by integrating this equation, we can obtain the drag and lift force. Okay, however, to integrate for a simpler body like flat plate, okay, so it can be, we can use this equation in order to obtain drag or lift. However, for complex body like your car, like your motorcycle, like airplane, so it is considered as a complex shape, so this analytical of drag and lift cannot be used. Okay, so you can see how we can determine the theta for the car. Okay, so how to determine the wall shear stress around the car. Okay, so that's why analytical cannot be used for a complex body or complex shape. Okay, but the fundamental of integration of this drag and lift is used in the numerical simulation and also in experimental or in wind tunnel simulation. Okay, so in order to solve for these methods in analytical, so we come out with the dimensionless of lift and drag, which is called lift coefficient and drag coefficient. Okay, so lift coefficient basically it is equal to lift force divided by half rho u squared multiplied by area. Okay, half rho u square is dynamic pressure. So remember your Bernoulli equation. There are dynamic pressure in Bernoulli equation, while for the drag coefficient d, which is drag force, divided by half rho u square a. Okay, so u is the incoming velocity or uniform velocity or upstream velocity, and then a is the area. Okay, a is area. So what is the area for the complex body? Okay, so as you can see in this figure, for the F-foil, normally for the F-foil, so as you can see this F-foil, the area is taken from the planform area, which is C multiplied by the length of this F-foil. Okay, and then for the blunt or bluff body like car, normally we use frontal area, okay, which is A, the thickness multiplied by the length. Okay, so this is how we determine the characteristic area in order to determine the lift coefficient and drag coefficient. So in this part, it is related to characteristic of flow past an object. Basically, for the moving object, we can characterize the flow. Of course, based on the shape of the body, of the shape of car, for example, shape of airplane, and then we can characterize based on size. Okay, how long your car. Okay, for the truck, how long the truck, and then the speed, the coming velocity. And of course it is depend also on the fluid properties, okay, because fluid properties play an important part. Okay, fluid properties, for example, the viscosity. Okay, so it is plays an important part for the to characterize the flow. So for all these various parameter, it is now combined in only one dimensionless number, which is called Reynolds number. Okay, so for typical external flow, the most important of this all dimension parameter are the Reynolds number, which is rho u l divided by mu, or it is also equal to ul divided by nu, which is kinematic viscosity and dynamic viscosity. Okay, so rho is rho for the fluid, and then u is the velocity for the incoming velocity, and then L is the characteristic length. Okay, so characteristic length normally for the F-foil, it is the chord length, which is defined as a characteristic length. And then we can define also in terms of Mach number. Okay, Mach number is the ratio between u and c, which is speed of sound. On top of that, for flows with a free surface, in the example, flows with an interface between two fluids, such as the flow past a surface ship. Okay, so the Faraday number of Fr is normally been used to characterize the flow. Okay, Fr equal to u g multiplied by L. So these most external flows are associated with moderately sized object with a characteristic length on the order of higher than 0.01 meter and less than 10 meter. Okay, so in addition, in terms of upstream velocity, in order of u higher than 0.01 meter per second and then less than 100 meter per second, and then the fluid involved normally water or air. Okay, so for the ship, of course, it is water, but for the ship it involved with two kind of fluid, which is part of the ship is submerged in the water, and then part of it immersed in around the air. Okay, for the completely submerged in water is only submarine. Okay, so typically flow with Reynolds number larger than 100, it is dominated by initial effect. Okay, so the initial effect means that the u, which is the incoming velocity, and then whereas flow with Reynolds number less than 1 are denominated by viscous effect. Hence, most familiar external flow are basically dominated by inertia. Okay, so from the Reynolds number, we can characterize based on the effect of viscous, and in the effect of inertia forces. Okay, so in order to understand the effect of Reynolds number to the body, okay, so three plate with different Reynolds number is shown in this next slide. Okay, so for first one, flow past a flat plate at Reynolds number 0.1, which is less than 1. So as you can see in this figure, so this is the plate with length, the characteristic length is L, and then this region, basically this is where the viscous region, where the viscous are very important. Okay, so mean that for the very low Reynolds number, the viscous region is really dominant. Okay, so really dominant, as you can see in head of the plate there are viscous region, and then top and bottom of the plate there are still viscous region, and then in the wake or behind the plate there are still the wake region, and then the streamline deflected considerably. Okay, for this Reynolds number. Okay, so if the Reynolds number is small, the viscous effect are relatively strong, and the plate affect the uniform upstream flow far ahead. Okay, above, okay, as I mentioned, below and behind the plate. So to reach that portion of the flow field where the velocity has been altered, okay, the coming velocity has been altered in this region, less than 1% of its undisturbed value. Okay, if for example the u is coming velocity, and then u in this region, in this viscous region, we must travel relatively far from the plate. Okay, so it can be concluded that for low Reynolds number flow, viscous effects are felt far from the object. Okay, so that is for very low Reynolds number. Okay, so very low Reynolds number, you have bear in mind the viscous are very dominant compared to the initial force. Okay, what happen if we increase the Reynolds number? Okay, consider the same plate, but now the Reynolds number is increased to 10. Okay, so as you can see, the major difference between this Reynolds number, for the 0.1 Reynolds number and 10, is about the region of the viscous region. Okay, so the viscous region is now becomes smaller compared to Reynolds number 0.1. Okay, so as the Reynolds number is increased by increasing u, for example, the region in which viscous effect are important becomes smaller in all direction except downstream. Okay, so the region in which viscous effect are important becomes smaller except downstream. Okay, behind the plate, it is still the distance is still like Reynolds number 0.1. Okay, and then streamline also deflected somewhat. Okay, so there are deflection. Basically this deflection is due to the interaction of the viscous boundary layer in this region. And then what happens if we increase to a very high Reynolds number? Okay, so for very high Reynolds number 10 power of 7, as you can see, of course, first we can see that no more viscous region ahead of this plate. Okay, in fact the viscous region start somewhere at this location. Okay, not at the leading edge, or at the leading edge of this flat plate. Okay, so the wake region still exists, but the top and bottom are smaller, much smaller than Reynolds number 10 and Reynolds number 0.1. Okay, so mean that as we increase the Reynolds number to a very high Reynolds number, thin boundary layer may be developed in large Reynolds number flows. Okay, so if the Reynolds number is large enough, the flow is dominated by initial effect. Okay, at this region, the flow is dominated by the incoming velocity, which is the initial effect. Okay, and then the viscous effect are negligible everywhere except in the very thin region close to the plate. Okay, so the fluid must stick to the solid surface where the no slip boundary condition is detected, or no slip boundary condition must be used. Okay, so there is a thin boundary layer region of thickness delta equal to delta x much less than length, which is thin relative to the length of the plate, next to the plate in which the fluid velocity changes from the upstream value of u, okay, from of u to zero velocity on the plate. Okay, the thickness of this layer increases. Okay, so the thickness of the boundary layer increase in the direction of flow. Okay, so as the flow moving downstream, the thin boundary layer also, the thickness of the boundary layer also increase. The flow within the boundary layer may be laminar, so it can be laminar or turbulent depending on various parameters involved. Okay, so this is related. This is this three slide basically to show what is the difference between Reynolds number, which is a very small Reynolds number, to a very high Reynolds number over a flat plate. Okay, and then now what happened to a bluff body like a cylinder, okay, like a circular cylinder, when we varied the Reynolds number. Okay, so as you can see in this figure, the Reynolds number is now u d over v, or over viscosity over nu, where d is now is the characteristic of length for the cylinder. Okay, so as you can see in this figure, the Reynolds number is very small, 0.1, and then even though the shape is complex, it is considered complex, but the symmetrical streamline still can be captured based on the Reynolds number equal to 0.1. Okay, so the presence of the cylinder and the accompanying viscous effect fell throughout a relatively large portion of the fluid. Okay, so the viscous region is still large, and then the viscous effect are important several diameters in any direction from the cylinder. Okay, so the diameter is d, the diameter of cylinder is d, but the dominant of the viscous region is sometimes much larger than diameter of this cylinder in the top, in the ahead of the upstream of the cylinder and downstream of the cylinder. And then, as I mentioned, the streamline are essentially symmetric about the center of the cylinder, and then the streamline pattern is the same in front of the cylinder as it is behind the cylinder. So this is where what happened, even though we use a bluff body, however, when the Reynolds number is still very small, we can still obtain this symmetrical streamline. Okay, and then now we increase the Reynolds number to 50. Okay, so when we increase the Reynolds number to 50, the region is now, as you can see, the region ahead of the cylinder is now decreased. Okay, the region ahead of the cylinder is now decreased, and then this region is now moving downstream of the cylinder. Okay, so as you can see in the wake region behind the cylinder, the region is increased. Okay, so the viscous effects are convected downstream. Okay, and the flow lost its upstream to downstream symmetry. Okay, and then the flow separate from the body at the separation location. Okay, at the Reynolds number 50, the symmetrical streamline cannot be captured anymore, and then in the wake region behind the body, there are separation happen. Okay, so at this separation location. Okay, and then a separation bubble behind the cylinder. Okay, so this is separation bubble in which some of the fluid is actually flowing upstream. Okay, suppose the flow is flowing downstream, but due to the separation, the flow is now flowing upstream. Okay, upstream, and then against the direction of the uniform of the upstream flow. Okay, so this is for the Reynolds number 50. But what happened to when we still increase the Reynolds number to a very high Reynolds number? Now Reynolds number is 10 power 5. Okay, so as you can see in this region, the wake region, the viscous region is very small compared to Reynolds number 50 and Reynolds number 0.1. And then of course the symmetrical streamline cannot be captured anymore. Okay, and then the separated region is also much larger. Okay, and then the wake region behind the body is also large compared to Reynolds number 0.1. Okay, so the area affected by the viscous force is force closer to the cylinder until it involves only a thin delta. Delta is thinness boundary layer, very much smaller than the boundary layer on the front portion of the cylinder, and irregular, unsteady, perhaps turbulent wake region that extend far downstream of the cylinder. Okay, this is wake region which is far downstream of the cylinder. Okay, so in this phenomena, the velocity gradient. Okay, so recall velocity gradient in chapter 1. Okay, so the velocity gradients within the boundary layer and wake region are much larger than those in the remainder of the flow field. Since the shear stress for this velocity gradient, which is much larger than those in the remainder of the flow field, in that in the inviscid or viscosity not important. Since the shear stress, in example viscous effect, is the product of the fluid viscosity and the velocity gradient, so it follows that viscous effect are confined to the boundary layer and also wake region. Okay, so viscous effect is now not only in the boundary layer, but it also confined back to the wake region. Okay, so shear stress, so recall shear stress tau equal to mu du dy. So this is that definition. So du dy is velocity gradient. So velocity gradient in this region, in this very thin region, is really high. Okay, compared to those that are not that viscosity is not important. Okay, so the characteristic of this thin boundary layer will be covered in the next part, the next subtopic of this chapter. Okay, so what happened inside the boundary layer, and then how to determine the type of flow, which is laminar, for example transition and also turbulent, and then how to characterize the flow separation based on the pressure difference and then pressure gradient. Okay, and then for the last slide, okay, so for the conclusion, the larger the Reynolds number, the smaller the region of the flow field in which viscous effects are important. Okay, so for objects that are not sufficiently streamlined, however, an additional characteristic of the flow is observed, which is termed flow separation. Okay, so as you can see in beginning from Reynolds number 50, basically 50, where the streamline is not symmetrical anymore, you can observe a new fluid flow phenomena, which is termed a flow separation. Okay, so now, as I mentioned in the beginning of this lecture, how to obtain, what happened to a body when it is a very streamlined shape. Okay, so this is kayak. So kayak is a body or vehicle that is that consists of a streamlined body. Okay, so that's why it is really easy to move the kayak. Okay, so what the Reynolds number around this blade is really high, because this blade is very important in order to move the kayak. Okay, so now what happened? This is a moving person inside this tunnel. Okay, so what we want to show that even though the moving is very slow, but the weight behind the person is very large. So I mean that the Reynolds number is not only depending on the on the velocity. Okay, so I think that's all for introductory for the immersed flow immersed body. Thank you.